Hey there, awesome physics students. Let's talk about the Doppler effect. The Doppler effect is when you have a source of some waves moving relative to the receiver of those waves, and the receiver will perceive a different frequency than is emitted at the source because of that relative motion. Let's talk about a situation with sound. So imagine that there's a person in a car and they're just sitting in the parking lot and they're holding their hand on the horn for several seconds and they're not moving, so the velocity of that person is 0 in the car. So let's look back in time 3 seconds ago to see where the wavefronts from the emitted sound are. Of course, they're going to travel in all 3 dimensions, away in a spherical shape, away from the source of the sound. Now, if we look back 2 seconds ago in the past, the car is still here because the velocity is 0. And so those wavefronts will have traveled away from the source of the sound, but they won't have traveled as far. And if, again, we look back 1 second in time, then those wavefronts will have traveled less distance. But of course, these are all concentric. They're all centered on that one point because the velocity is 0. If, on the other hand, we imagine a car moving on level ground, so we can draw its motion diagram like this. Its velocity will be to the right, like that. If we look back 3 seconds ago in the past, the car was here. The wavefronts have traveled out, centered on that point, and so they're going to look something like that. If you look back in time 2 seconds ago, of course, the car has shifted its position, and so the wavefronts will be centered on this point, and they will have traveled some distance away from that center point. If you look back in time 1 second ago, the car has shifted its position again, and the wavefronts will be centered here. Of course, they haven't traveled as far because they haven't had as much time. So if you're a person that's standing right here, what you see is these wavefronts have appeared to bunch up. The arrival time between these wavefronts is lower than what it would be if the car was still. And so the period of these wavefronts is lower, or the frequency is higher, because the frequency and the period are inversely related. If, on the other hand, you're standing over here and the car is moving this way away from you, what you perceive is the wavefronts are separated with longer periods of time before they arrive at your ear. And so you perceive the period as being a larger period or a lower frequency. So remember, a higher frequency is like that, and a lower frequency is like that. And so if you're standing here when the car is driving towards you, you hear the horn as much higher. And then as the car passes you, you hear it suddenly shift. You become this person, and you hear it shift to a lower frequency. And so you perceive that frequency shift because of the Doppler effect. Now, this is true for not just sound waves, but all different waves, light waves included.